Happy day to you, friends. We're going to go ahead and get started today with a quick reminder of PLC 11 this week and homework 5, which hopefully you've had a bit of time to at least take a look at and see how that's going to shape up for you. That's going to go for a week from tomorrow as I'm recording here. This is for Thursday the 23rd, same day as Celebration 2. And we will go from there because we'll probably get through today and tomorrow, and I think that will probably be it. I'm just trying to foresee the amount of time that we need here, but it seems as though we might be just finishing off things by the end of this week. And that way we won't have to go into next week for any of the material for Celebration 2. So we'll see how we do. And in order to make that happen, I'll go ahead and get started with some more of the stuff we were talking about. Now, when it comes to second law, we've talked about the statements that people have made about the second law. And one of the statements that is really well known, but isn't technically a statement of the second law of thermodynamics, is the idea of the increase of the entropy. And last we left off, we were introducing the idea of entropy as a state variable. So let's go ahead and take a quick look back here at the quantity of entropy. So just to remind you, right, it's a state variable. In other words, it has a specific quantity. I mean, it has a specific value at every point when the when you look at the PV graph, right? Just like we would say the internal energy has a value at a particular point on the PV graph. So, right, if I pick a point on the PV graph, I would say, well, there's energy, there's a particular pressure and volume that's defined for that, there's a temperature that's defined here, right? There are things that are defined here, E internal, and also now S, which is the entropy, okay? When you look at the first law, however, it's telling you that the change in internal energy is due to Q plus W, and what that's basically indicating is that as you go from one place to another on the PV diagram, there's a change, possibly, in the internal energy, and that change is due to heat added or work done. Those things are not state variables, however, they are due to the path taken between the two states. So if I call this state 1 and state 2 over here, there's a definite internal energy difference between the two states, and that won't change. What could change, however, is the heat transferred and the work done based on the different paths I take, right? If I take a path that looks like this, like that, that's going to be a certain amount of work. If I go down this way and then like this way, that's a different amount of work. Right? Because think about the work is the area underneath these things. There's different amounts of work going on here. So, and you could also just do something pretty straightforward. Like come over like this and go down like this, right? There's a whole different amount of work done by that path than if I had just gone straight. These two, Q and W, are therefore dependent on how I go from 1 to 2, but E internal, the delta E internal is not, and likewise, neither is delta S. Delta S, if you recall, is from 1 to 2 of dq over t. So what this is getting at is that there's an entropy defined at each of the points, and how you find that change in the entropy is by examining what the heat transferred was during the path. So let's take a look at a couple of ways of calculating what the entropy is as we go from one state to another state. All All right, so for example, these are all crazy paths, right? And we would never do something like this if we want to actually do a calculation of something. So one way to do things is to do them in a very straightforward manner, which is to say, well, suppose that I dropped the pressure from state 1 down to here in a constant volume way, and then I increased the volume here at constant pressure. So suppose I took these two paths to go from 1 to 2. That's a constant pressure process. This is a constant volume process. And these are the two that we've worked with pretty well, as we've been doing with the PV processes. So let's take a look. If I consider transferring heat at constant volume, I would know how to calculate that heat, right? So if I think about constant volume as one of the ways I'm transferring heat, since I have, I don't know, a certain amount of ideal gas here, I would say a mole of a monatomic ideal gas, which is a nice way to do about it. If I have 1 mole of monatomic ideal gas, then I know how to calculate monatomic. Then I know how to calculate what the heat transferred is as I drop from the initial state down to the pressure of whatever the state 2 is here, and then I got to expand and go out to state 2. The amount of heat transferred then would be just our molar specific heat at constant volume times N and delta T, right? In exact analogy to the MC delta T, okay? So that would be a constant volume, and therefore I could write a dQ for that, which would just be, since temperature is the only thing changing here, that would just end up being a dt in how I'm doing this. Okay? Now, knowing that I have 1 mole of a monatomic ideal gas, I can rearrange this a little bit to come up with it being essentially just 3/2 R dt. And you can see that this 3/2 R is just a constant. If I then want to find out what is the change in entropy as I drop from state 1 down to the pressure of state 2, I could now do that by saying that delta S from, I'll call this an intermediate state, like state A or something here, so that I can label this. So this is the entropy change going from 1 to A would just be the integration of dq, which is now this thing, divided by T, from 1 to 2. It would, right, I would need to know what these temperatures are, but effectively I'm going to be integrating temperature from T1 to TA, right? So I do this. As I drop that, I'm removing heat from the gas in order to do that. The 3/2 R as a constant comes out, and you can recognize the dt over T as a natural log, and therefore, I forgot an equal sign here, and therefore I'm going to get 3/2 R times natural log of TA over T1. All right, a quick eyeball of this is going to tell you that that's going to be a negative. In other words, if I consider my isotherms on the PV diagram here, temperature at 1 should be at a higher temperature than temperature at A. Okay? Temperature here at point 2, I don't know quite what that's going to be, but we can also do the same type of analysis at constant pressure, because we have a constant pressure specific heat as we just did with the constant volume here. Okay? Now, what I want to say here about this is that this is definitely going to be a negative number, right? Because the natural log of this ratio is going to give me a minus sign in the final answer here. So 1A or 1,2A is going to be less than 0. And the reason for that is because I removed heat from the ideal gas. Now, how does that make sense? Well, the way you think of heat, or maybe the way I think of heat, maybe is a better way to put this, is that heat causes a more disordered state. If I put heat into something, it causes more randomness. And entropy, ultimately, I was leaving you with the thought last time that entropy is essentially a measure of the quality of the energy. And if the energy is, for lack of a better term, well organized, then the entropy is low. If the energy is highly disorganized, then the entropy is high. That's why heat is the major player in determining how much of an increase there is in the entropy. When I add heat to something, I increase the random craziness of how the particles are moving about. When I take it away, I lower that down. So this is going to be a negative because it's kind of going towards a bit more order. I've removed heat from something, and therefore the molecules have perhaps slowed down a bit. The temperature has dropped. Things could be a little bit more organized than they were, a little less crazy disorder. So one of the statements of the second law, it has to do with the increase of entropy. And we find, in general, that the entropy of the system that you're talking about generally always increases. I have therefore contravened that law here with this statement and the findings of this process. And the reason for that is because I'm looking only at the system of the monatomic ideal gas. Now, it's totally possible to increase or decrease the entropy of things in isolation because I'm looking only at that system. I'm looking only at that small piece as the system. I'm not looking at what it's interacting with. Okay. When you think about heat and the transfer of heat, this is energy, right? So that energy has to go somewhere. I can't just take the energy away from the ideal gas and suddenly say, poof, it's no longer here. When I take that heat away from the ideal gas and I put it somewhere else, guess what that does to the entropy of the somewhere else, right? There's going to be an increase over there. So just because the entropy of some part of something drops does not necessarily violate the kind of commonly held idea that entropy always increases. Okay, entropy always increases, but you have to look at all of the interacting parts. This is very much like the thinking that perhaps you learned in 4A with the conservation laws. And you can certainly use energy as an example of that, or momentum if you like. The idea, our belief is that energy doesn't just appear or disappear, it goes somewhere. Okay, so I could, for example, take the heat away from this ideal gas, but we know that it has gone somewhere. We have to deal with it. We haven't had it just poof away into nothingness. So the same kind of thinking is true here with the entropy. The idea being that the entropy of the ideal gas dropped, but when I took that energy and I put it somewhere else, that's an interaction and therefore leads to an entropy increase in the place where I put that heat. All right. So when you consider the idea that the entropy increases, it's basically the idea that the quality of the energy that we have decreases. Or a more common way to think about it is that the disorder of a system increases, right? If you consider entropy to be a measure of the disorder of the system, okay, then an increase in the entropy means an increase in the disorder. And hence, that's why this chaos will reign, turns into kind of a more funny way of thinking with the second law. Okay, so a kind of common way of thinking here, or the common second law, is that entropy of a system Well, I should say, it doesn't always. It never decreases. But with that being said, you have to be careful about your system, okay? So what I was saying about the energy is that the energy of a system can change. And you'd say, well, wait a minute, isn't energy supposed to be conserved? Yeah, but that means if you find that energy is not conserved, you haven't looked at the bigger picture. You haven't looked at a big enough picture. And the same thing goes here. If you find that the entropy decreases, then you haven't looked at a big enough picture, okay? So that means that the idea of the system here has to include all interacting parts. And if you have a heat transfer, you have two pieces to think about, right? Where the heat came from and where the heat is going. And therefore, you have to be kind of careful with this. Has to be all the interacting parts. You can't just decide to not look at something, especially if you want to apply that law. Okay, so this is one way to think about doing a entropy calculation, is by taking a differential of the Q, and in general, it's a fairly straightforward process in the way that you can generally see what is the differential going to operate on, right? In other words, if I take a small bit of heat, it's going to lead to a small temperature change when I'm talking about constant volume here, right? If I'm talking about constant pressure, well, a small bit of heat leads to two things, right? An increase, if I'm talking about going this way, it's going to be an increase in the temperature, but also an increase in the volume. More volume leads to more randomness, right? There's more space to be disordered in. If you think of the gas molecules as basically being like a pack of birds or wild dogs or something like that, well, if you have them in a small space, you have them fairly well confined, and there's not a lot of order in that. But if you let them range over a larger area, there's going to be a lot more disorder. They're going to be, right? They're going to be making all sorts of chaos all over this bigger area rather than just having it in a small confined area. So a larger volume of a gas, for example, will lead to larger entropy because there's more room to be disordered in. This is kind of the way of thinking about that. Okay, so I thought one thing we could do is take a look at another quick example here, one that's got a little bit more of a concreteness to it, which perhaps would be good. In which I'm going to look at a liquid water drop, and I'm going to look at a specific interesting process that can happen during a liquid water as it freezes. So let's assume that I have a liquid water drop, and I have managed somehow to cool this liquid water drop to below 0 centigrade. And this is certainly a thing that can happen. If you've ever seen, or if you've ever seen videos on stuff like this, or you've actually done it, it can happen with very, very pure water, ones with very little mineral content in them, or anything like that. So if you have a bottle of very pure water, sometimes you can do this with one of those plastic bottles, and you put it in the freezer. What'll happen, or what could happen, is that the temperature drops to below the freezing temperature, but because the water is so pure, it stays as a liquid, which is kind of a crazy thing. It's known as supercooling. You've cooled it, but you've cooled it below the freezing point, and it has remained as a liquid. I want to take a look at the entropy of a supercooled water droplet and see if we can just do a few calculations. So let's make the water droplet fairly easy to deal with. Let's suppose I have a 1 gram water droplet. And I'm going to cool it to below 0 centigrade, something pretty easy like maybe 5 below centigrade. But then all of a sudden, it freezes for some reason. It all of a sudden goes, oh, the other part to that, if you've seen the videos of the supercooler, right? You bang the water bottle, or you do something to the water bottle, and all of a sudden you can see it, and it's almost like drawing curtains. It's like the solid suddenly just starts, and it expands, and all this fills up the whole thing. It's pretty cool. If you've never seen something like that, go check that out. I'm sure there are plenty of YouTube videos on supercooled water or something like that. Kind of fun to watch. Suppose that this starts at -5 centigrade. I had it in the freezer, and now I'm going to take it carefully out of the freezer, and I'm going to agitate this water droplet somehow such that it freezes. Okay, it undergoes freezing. And suppose that, suppose I didn't take it out of the freezer. Suppose I just left it in the freezer and I agitated it, but we were in the freezer. So suppose it's going to cool back off to -5. Okay, because why do I say cooling back down to -5? It was already there. Well, because when it undergoes freezing, it does so at 0 centigrade. Therefore, it had to have warmed, frozen, and now cooled back off. Because this freezing has to have happened at 0 centigrade. Let's calculate the entropy change for this. And I'm going to look only at the droplet. I'm going to look only at the droplet, which means I have a very narrow view of the system. And therefore, I would expect my entropy change, it could be plus, minus, or 0. If I'm looking only at one thing, it doesn't necessarily have to always obey this, because I'm not looking at all the interacting parts here. Okay? So in this case, I could expect anything from the sign of the entropy change. If I look at the gram of water, then what is its behavior? What has it undergone? It started here at -5 centigrade, and it immediately, when agitated, had to have increased its temperature to 0. So the first thing it does is we had 1 gram of water going from, it goes from -5 centigrade to 0 centigrade, because that's where it's going to change temperature. It's then going to freeze at 0 centigrade. And it's then going to drop back down to -5 centigrade again. Therefore, I have 3 entropy changes to calculate. Okay, 1, 2, and 3. This temperature change here is a sensible heat transfer. So we know how to calculate the Q for that. Okay, I'm going to try and calculate delta S being dQ over T for each one of these. All right, now this first one and this last one have changing temperatures, so I have to be careful with how I deal with the temperature here, just kind of like I did with the ideal gas example there. But look what happens in the middle. The freezing happens at a given temperature, so that is a situation where the temperature is constant and can be removed from the integration. So let's start with the easy one. Okay, let's do the easy one. Freezing. This is a latent heat transfer. Therefore, if I think of dq over t, the t is constant, and therefore it just becomes q over t. Like I was telling you yesterday, when I remove the t from the integral, I integrate dq. I could do that all day. I love integrating dq. I'll do that all day. We know, however, that during a freezing process, that latent heat is what the Q is. I can re-represent that Q as equal to M times L because it's freezing. That's a latent heat transfer. Furthermore, that heat had to have left the droplet, right? That's heat that is leaving. So really, that would be a negative. According to the droplet, that heat's going away from it. So the delta S, can I just call this, let's say, stage 1, 2, and 3. So this is delta S for 2. Okay, let's just label that as a 2 here. So I can just say that it's this part here. Delta S for part 2 would be negative Q over T, which means it's negative ML divided by temperature. Now, good news here is that we know the mass of the droplet that froze. The latent heat of freezing for water, we know what that is. And if you don't know what it is, that's fine, but it's a given. We don't need to worry about trying to calculate that. That's something that we can look up. And the temperature at which it happens, we also know. Now be careful, we're not going to be doing 0 centigrade for obvious reasons here. We do want to be working in the Kelvin scale, so that'll be divided by 273. Now, if I look at sections or stages 1 and 3, I can come up with a dq over t for these. Let's suppose I'm going to start with delta S for 1. And I am again going to recognize that this is a sensible heat transfer in which the temperature changed, and therefore I can represent that heat as an mc delta t, but I want a dq, so I'm going to use a dt. Much in the same way as I just did with the ideal gas. This, therefore, is going to turn into an mc dt over t. And it turns into a temperature integration where we started at -5 and we're going to 0. Call that T1 and T2 or something like that. Now, careful, I've got the 1 gram for the mass here. That C, be careful here, this was a liquid state here. This has to be the liquid water specific heat. When it goes back from 0 to -5, now it's ice. It's solid water, so I have a different specific heat for this part. Okay, nonetheless, the form of it will look exactly the same. It'll still be a sensible heat transfer, and all the math that I'm doing here symbolically will transfer directly from, or it'll apply directly to section 3 here. All right, so this is going to turn into, once again, MC. I'm going to get the natural log of T2 over T1. In this case, T2 is the freezing temperature, T1 was the starting temperature, so this is going to be a positive number. This is an increase in the entropy as you might expect it to be, because the temperature went up due to heat that it absorbed from its freezing. Okay. So if I think about delta S1, it looks like this. It's going to become a positive number here. If I think about delta S3, it should look exactly the same symbolically as that. But I'm going to use the temperatures of, and also I should also be careful. I'm going to do the C for liquid, and this is the C for ice. C liquid and C ice. I should have used, whatever, C solid. Delta S3 should be the same log, but in this case, the T2 I was calling to be the 0 and T1 was the -5. So really, if I use the same variables for the numbers here, right? In other words, this is T2 and this is T1. That means in this case, that's T2 and that's T1. If I call them the same thing, I know it's final and initial, but it's going to be flipped because I did it the other way here. Therefore, this is going to be T1 over T2 because I end at the -5 temperature, which is my final, and that should be final divided by initial. So it's final divided by initial, and I call T1 the final. You can, again, notice this is probably easy to see that that's going to be a negative number in the log because of the ratio being less than 1. So this is going to turn out to be a drop in the entropy, right? In accordance with the idea that removing heat causes less disorder. Ultimately then, the droplet's entire change in entropy is going to be 1 plus 2 plus 3. And so I can, in fact, calculate all of those. That's going to be the liquid times the log of T2. What did I call it? T2 to T1? Minus ml over T. And now that T that I'm talking about, which one is it? It's T2. And I've also got here left over, I've got the ice specific heat, I've got the log, and I can be tricky about this and bring my negative sign out and flip over the ratio if I wanted, rather than adding what I already know is a negative number. I really have an issue. This is just me doing this. I don't want to add things that I know are already negative. I'm just going to pull the minus out and work with the absolute values of it. So it says this, but I know that that log is a negative number, so I'm going to flip the ratio and pull the negative explicitly out to the front here. And so we can calculate these numbers. What do we think is going to happen here? Well, this is an increase in the entropy. These are both decreases in the entropy. And the mass is 1, so that's no big deal. I can plug all these numbers in. This is common, right? We have a common set of factors here. So really, I could just do Cl minus Ci and multiply that whole thing by the log of the ratio of the temperatures here. Since the mass just equals 1, I guess I could do that too, but T2 over T1. Nope, T2. There we go. Like that? Seems like that'll work. This is 1 gram, so I'm going to work in grams. This is about 4.2, and this is about 2.1. The log here goes T2 over T1, which is 273 over 268. And the negative 1 gram. The freezing, the heat to freeze a gram of water is 333 joules you have to remove. And this is going to be in Kelvin. All right, so this number here, I'm guessing, is going to be a negative number because this, this log is going to be a pretty small number. It's going to be pretty, this is a ratio close to 1, so this is going to be a number that's going to be close to, well, it's going to be between 0 and 1. This is a number about 4, but this is a number that's 300 divided by 200, so this is a number that's about 1. Oh, well, maybe it will be. Let's see here. I came out with, I got negative 1.2. And the question here is, well, what units are we talking about here for the entropy change? What units are we going to be talking about? Well, if you go back to how we defined it, which I just erased, but if we go back to this, you're going to see that the units of the heat are going to be in joules, the units of the temperature in Kelvin. And so this is going to be the joule per Kelvin. Right, which is giving you an idea of how much energy per temperature. It's a little bit convoluted in the sense that the units don't tell the full story here, but the measure of the entropy is going to be in the joule per Kelvin. And this does turn out to be negative, but we're okay with that, because we know we're only looking at the droplet here, which means I have ignored the surroundings, okay? Definitely the surroundings, you would imagine, had to have increased in entropy, at least at this rate, likely much more than this, okay? So that the droplet, which gained a little bit of order from its freezing, right? It gains order from its freezing, but lost a little bit because of its temperature increase, and gained a little bit because its temperature decreased. So that freezing really was the dominating term here, it looks like. Because what happened, thinking about what happened in terms of ordering of the system, right? Ordering of the system, when you go from liquid, which is fairly random, right? You got molecules slipping past other ones, they're kind of moving around, lots of shear, versus a solid where everything's locked in place. The solid has a repeatable lattice structure to it, right? And you just see this thing, this shape is repeated. That's a very ordered structure. So a decrease in the entropy here kind of makes sense in the way of thinking of going from a liquid in a disordered state to a solid, more of an ordered state. All right. So that's a little bit on how to calculate the entropy of things just based on heat. Okay, so heat transfer causes entropy to change. Work does not cause the entropy to change, because work is already fairly, right? This is the ordered version of our energy. That's what we are gaining when we get more ordered energy, is like we have more energy available to do useful work for us. That's what the energy kind of goes to. That's the state that it goes to. When you want to do useful work with it, it has to be fairly low entropy energy. And unfortunately, the law of the common thinking of the law tells us the entropy always is increasing. So it's doing the opposite of what we really want. And what do you want me to say? That's nature for you. Okay. So that's a couple of things on how to calculate entropy of some situations. Let's see here. We'll do a couple more examples here. I thought we could talk a little bit more about the Carnot cycle and heat engines and refrigerators. Because ultimately these are the ones that we can calculate the coefficients of the efficiency for. All right. That is a specific word, meaning that, remember, we are considering a reversible cycle, one in which no entropy is generated. So I want to revisit this really quickly with the idea of thinking about entropy as the change in, or I should say as the change in entropy as a cycle goes on. So if you take a look at a heat engine, right, this word means that we are operating at the best possible, we're operating in the best possible state. This is the best possible situation, okay? And one of the reasons we look for the best possible situation is because that gives us the ceiling of what we can expect from efficiency in a given cycle that we might be interested in. Everything else is going to be lower than that. All right, so it's a nice, easy way to think about what could we expect to have happen, and go from there. So a heat engine, as you know, looks along the lines of this. Okay, heat transfer comes in, it's a large amount, or relatively, it's a large amount, some of which we siphon off for work, most of which, at least for us, most of which goes into exhaust, throwing away, right? This is waste heat that we are dumping. The word Carnot means, right, that we are operating at the best possible efficiency that there is, okay? Remember, the best possible efficiency that there is not 100%, because that's not even attainable according to the Carnot cycle. Remember, we talked about the theorems yesterday, that QC can never really be zero, because we always end up with dumping of heat here. So there's always going to be a loss or a waste that we don't use. There's no way to take all of this input heat and convert it into work. That 100% rate, that cannot happen. That's not even in the ballpark, okay? So when we're talking about getting to the best possible situation, the best possible situation is already less than 100% efficiency. And that Carnot efficiency, I told you this last time, the Carnot efficiency is this ratio of the temperatures, right? 1 minus the ratio of the temperatures. I wanted to explore a little bit on how we got to that, because we started with an efficiency of the heat engine, which is W over QH. And we came to the idea that by the first law of energy conservation, we could write it this way. And then we could write it with the ratio of the heats. Okay. And from there, we went to the Carnot and said that the ratio of the heats is the same as the ratio of the temperatures. Now, there's a lot of really cool reasoning and thinking that went into all of this, but ultimately we don't have time to explore that thread in great depth. So let me kind of cut to how this happens. I told you last time that we said that the Q over T's were equal. Here's what's going on. All right, now let's go back and take a look at this in terms of entropy, okay? So the delta S of a full cycle of this would involve a heat transfer from the hot reservoir, a heat transfer into the cold reservoir, and then this cycle right here, okay? So this has to include an entropy change from the H, it has to include an entropy change from the cold, and then it has to include the entropy change from the actual heat engine cycle itself, which is this thing. Okay, this is the heat engine cycle. That's the heat engine cycle. Therefore, any Carnot or any working heat engine like this is going to have these three entropy increases to think about. Okay, now, if we're talking about working at the Carnot heat engine level, then what we're talking about is having a reversible heat engine in which, remember, we have really managed to be so careful that we've arrived back at the original state exactly after having done all of these processes at isobaric and isovolumetric and isothermal and adiabatic, and then boom, we're right back to the very first state, which means that the change in entropy of the heat engine must be zero because we've been so careful to be reversible about everything, not incur any losses due to friction or noise or turbulence or we haven't done any of that. We've been really careful, and therefore, in the Carnot sense, that's equal to zero because we've done this in a reversible way. All right, we've done that reversibly. That means that the entropy change is really down to the entropy change due to the heat transfer from the hot and the heat transfer into the cold. Remember at the very beginning of this, I said these are reservoirs, which means that when you exchange heat with it, it's just a small little amount of heat compared to the great heat capacity of this body, and therefore the temperature of this we can consider to be constant. Yes, we're dumping heat into this thing, but effectively it's not changing the temperature. Therefore, if I think about the entropy change of the hot reservoir, it's happening at constant temperature. It's a loss of heat that happened at temperature TH. Therefore, this is negative QH over TH. This dump of heat, this is the dumping of waste heat into the cold reservoir. Remember, this doesn't change the temperature of the cold reservoir. So this is heat transfer at constant temperature. Must look like QC over TC. And since we have done everything as reversibly as possible, we want to operate at the very bare minimum of satisfying the second law. And the second law, the common second law, I erased it from up here, was that the entropy does not decrease. That is as low as you can go and not decrease. That's the very bare minimum, okay? And this is how you get to the idea of the heat ratio can be replaced by the temperature ratio if you are talking about something that is idealized and totally reversible, okay? When you think about Carnot, that's what should pop into mind, should be idealized and totally reversible. Okay, and therefore, when I think about just this efficiency here, which is true for any heat engine, it's not true, I mean, it is true for any heat engine. It's even still true for the Carnot heat engine. For the Carnot heat engine, we can go one step further, and this is only true for the Carnot heat engines. This is not true for any regular heat engine. But there's a big advantage to using this, because this is going to give you the highest possible efficiency that you could expect to operate between these two temperatures. So when the operating temperatures are those, whatever these are, any heat engine will never be better than a reversible one. And therefore, this is the best possible situation. All right. So it's built in. It's I don't know, it's built in quite the right word, but the idea is that if you use this, then you're not going to do better than that. Nothing can do better than that. This is true for any heat engine. This is true in general because it came from this, which is the definition of the efficiency of a heat engine. And therefore, this will still work for any heat engine. But if you want to find out how good you could have been doing, you got to go to this one. And even then, you can't really even do that well because we can't make totally reversible cycles. I wrote heat engines and refrigerators, so I'd like to explore the refrigerator really quickly, and then we'll do a quick example on linking stuff up with a refrigerator. So the refrigerator technically does not have what's called an efficiency, because efficiency is a number which is always less than 1, right? You can see, since this is the best possible situation, and from the third law of thermodynamics, TC can never be 0. We can't approach, we can approach 0 Kelvin, but we cannot attain 0 Kelvin. There's always going to be some dump of heat into a non-zero temperature body or temperature reservoir. Therefore, this efficiency is always necessarily between 0 and 1. Well, I mean, I guess it could be 0 if you really wanted it to be. Just make TC equal to TH, then you can't do anything, right? Well, it's not really useful. So, okay, technically the efficiency could be 0, but it can't be 1. So when it comes to refrigerators, that's not the situation. The refrigerators have a different quantity. A refrigerator does not operate, it's not called efficiency. Okay, it's not called efficiency. Oh, whoops. Apparently I have not plugged in my computer. Okay. All right, there we go. It's not called efficiency. Instead, it's called the coefficient of performance. It's called the coefficient of performance. Since that's a lot to say, it's just called the COP, the COP. Whenever you're talking about a COP, that's a situation where you could expect that the quote-unquote efficiency is more than 1. COPs, this could be COP for a refrigerator, could also be useful for what's known as the heat pump. Also is useful for the heat pump. So you'll often see this as COPR or COPHP or something like that. Can be greater than 1. And honestly, if it is close to 1, you have a crappy refrigerator. Really, this should be a number that's like 5 or something like that. Why? Okay, let's explore. So why? When you look at the COP, let's look at a refrigerator here. The COP of a refrigerator. Well, let's go back to a refrigerator quickly. And what does a refrigerator look like? Well, it does this. Backwards, backwards, and backwards, like so. And therefore, really, by the quick and dirty definition of efficiency that I gave you last time, the purpose of the refrigerator is try to keep the TC at TC. It's trying to exhaust heat from the cold. It doesn't care where it puts it, just gets rid of it. Its purpose is this QC, and the W is the input that I had to use in order to get the QC out of the temperature of the cold side here, okay? Just by quick aside, I mentioned heat pump right up there. The purpose of the heat pump, this is also a heat pump cycle right here. But the purpose of the heat pump is QH. That's the thing that you want. So in other words, you could use this to heat a warm house already, right? If it's cold outside and you want your house to be warm, then you will use what's called a heat pump, and this QH is the thing that you now want. And W is still the thing that you put in order to get that. It's kind of crazy to think about, but the amount of heat that you're moving should be a lot greater than the work that you're putting in to do it. It's kind of a weird thing to think about. All right, but we're going to look for the refrigerator. The refrigerator coefficient is QC, that's what we want, and W was what we put in order to get the QC moved, okay? So if I do this, I would go to QC, and I can rewrite, well, I could rewrite QC in terms of the work, I suppose. I was just thinking of doing the work in terms of the heats. But I suppose we could do that, right? Again, still notice here that the ins must equal the outs, so QH has to equal QC plus W. And therefore, QC would be equal to QH minus W. So I guess you could do it this way. It'd be kind of weird. QH minus W over W, which means it's equal to QH over W minus 1. I don't know if that actually helps at all, but you should see that this is a number that's bigger than 1, right? It comes out, this QH over W should be vastly greater than 1, so that your coefficient of performance comes out to be some number that's larger than 1. Your hope is that that's what happens. If I'm looking at it from the way that I was going to initially do it, you could also write this as QC over QH minus QC. In other words, I could solve for the work here and then just put that difference in the heats down here. This does not really help so much, except that if I apply the same reasoning here that I had when I was looking at the heat engine, and I said, well, the entropy increases and decreases are still balanced. That means that anytime I have, and this is a little bit more shady in some way, but anytime I have a QC or a QH, I can basically replace it with a TC or a TH. So for a Carnot, if I want a Carnot refrigerator, I can make this into a Carnot refrigerator by basically replacing the Q's with T's. Like so. Let's do this. Okay. And so the same thing that I just erased would apply here. This would be the best possible coefficient of performance for any refrigerator operating between these two temperatures. Same thing, right? This is true for a real or Carnot refrigerator. This is true only for the Carnot refrigerator. And you could take a look at this. You could take a look at this and make a quick estimate. So suppose that you have your refrigerators probably, refrigerators are usually pretty close to about 40 degrees Fahrenheit, right? Maybe 42 degrees. That's around 5 centigrade or so. All right. So, and the hot temperature out here, room temperature, is maybe 20. So let's take a quick look. Let's make an estimate of just a regular refrigerator. What's the best that we could possibly hope for? If we look at the cold temperature being 5 centigrade and the hot temperature being, say, 20 centigrade. Okay. This means, now, of course, I'm not actually putting in centigrades into this, but rather kelvins. So this was going to look at 278 for that temperature. And then this is going to be a difference of, what is this a difference of? Oh, 20 minus 5. So this is this is okay to actually do as a centigrade, because if I add 273 to this and I add 273 to this, they're just going to go away anyways in the difference. So this is a difference of temperatures, so this is going to be 15. I can do it that way. Well, shoot, it's about 300 and that's about 15. So your coefficient of performance is around 2. It's less than 2. That's pretty bad. I mean, not 2, sorry, 20. That's actually okay. This is looking to be, 15 would be 225. So this is looking to be around, say, 18 or something like that. I don't know what it is, but that's what I mean. When you expect the coefficient of performance to be a large number, you expect the efficiency of the heat engine to be a number less than 1, but greater than 0. You're going to be different in how you think about these. So let's do an example of why the coefficient of performance is so big. Okay, let's take a look and see if we can look at a regular, or not a regular, let's look at a refrigerator and see what numbers we can come up with. So I cooked up an example here of what? What did I cook an example of? Maybe I have it here. Yes. Okay, so let's look at a Carnot refrigerator. Let's look at a Carnot refrigerator, because ultimately that's really what we want to do, is figure out what's the best possible situation. All right, let's assume here that I have a refrigerator that's powered by a Carnot cycle, and it's going to keep the temperature of the freezer. I guess I should have said freezer. It's going to take the temperature of the freezer at minus 15 centigrade. Really, it should be a freezer. Where I have this situation going on, and I know that TC is minus 15 centigrade. And while the while the refrigerator or the heat engine, while the thing is working to take heat out of TC, it's working. So normally you'd think of this as a rate, but let's just say we're looking at a specific amount of time. And so there's some number of joules that's going to get transferred out of the cold space this way. And let's suppose that QC is 40, let's just say 42 kilojoules. Right? All right. Maybe you could think of that as it happening during each cycle or something like that. Now, this is like one of those really big industrial freezers. Let's suppose the outside temperature out here is 30 centigrade. And it has a coefficient of performance of 6. Close enough. All right. So question, how much work am I putting in order to get this cycle to happen? And also, how much heat am I dumping into the 30 centigrade room, which is only getting warmer and warmer? And maybe you've experienced this, where you have these industrial freezers. Inside the freezer, right? You walk inside the freezer, obviously it's freezing cold. Not like any day that we have around here where my kids go, oh, it's freezing outside. I'm like, no, it's not. It's not freezing. But anyway, being pedantic aside, you walk out of the freezer and you have a little bit of adjustment, but you go, man, it's hot in here. Yeah, because what's happening? All of the heat that this thing is taking out is getting dumped into the room outside the freezer. So even if before you walk into the freezer, you walk into the room around the freezer, you go, man, it's hot in here. Yeah, it is. It's supposed to be. So let's see if we can calculate W and QC. Nope, QH. Find QH, because we already know what QC is. Alrighty. Couple of different ways to approach stuff like this. Always, you can think of the first law, right? I can always write out energy conservation like that, right? I can always say that those two coming in equal that one coming out.
I got new ways like this one.
So when I do that, I can say, once I find one of these, I can find the other one, right? What I can also do is use the coefficient of performance to try and see if I can determine, right, what we have going on straight from here. So if we do that, I can rearrange the coefficient to try and find the work pretty quickly. I can write QC over coefficient as a rearrangement of that. I'll find this is 42 kilojoules divided by 6. So the work per cycle is 7 kilojoules. That's what I'm talking about when I talk about the coefficient of performance. I'm putting in 7,000 joules in order to remove 42 from over there, which is great, right? And you'd wonder, wait, how can that be? How can I be moving so much heat with such a little input? Yeah, you can totally do this, okay? And it happens in electricity almost all the time. Basically, it's known as an amplifier, okay? You have a small input which causes the output to have an ability to be large, okay? It's not that you're contravening energy conservation, you're not. But you are able to affect a large flow this way by a small input this way, right? Another way to think about it would be, for example, if I have a huge water pipe, right? I have a huge pipe of water going along here, and it's all backed up, and it's trying to pump all this water through the pipe. But right here, I have a big door in the way. All I need to do then is grab this little piece and pull the door up, and all of a sudden all this water goes rushing through. Well, I didn't put in a huge amount of energy to just pull the door out of the way, did I? Not compared to pumping the water through. So for a small input, I can get this huge kind of result, okay? So that's kind of the same idea. When you look at this, then you'll be able to see from here, then whatever I had for the work, all I got to do is add that to the QC, and I'll get whatever heat's getting dumped into the room. And in that case, you'll see that it's going to be 49 kilojoules. Every cycle, the outside of the freezer is heating up due to that heat getting dumped into it, or it's maintaining a hotter temperature, whatever you like to think of it. But I'm dumping a lot of heat into this outside room, into the environment outside the freezer, and causing it to be really warm. Alrighty, so that looks pretty good. What was the other thing? Oh, I was going to talk real quickly about the heat pumps. So heat pumps, I was mentioning, same idea, okay? The heat pump is the same idea as this, but the effect is the QH. That's the thing we want, right? That's the thing we want, because we're trying to make the TH stay at that TH. If you imagine this is your house and you have a very cold night outside, then your house leaks heat, right? It's not rocket science. The heat's leaving your house through poor insulation. Or even if it's good insulation, it's still leaving, maybe just not quite so quickly. But your idea is you want to keep the temperature of your house to be about the same, even while the outside is extremely cold. So you, again, come up with this kind of strange, non-standard way of thinking of, how am I pumping heat from a very cold night into a hot house? Yeah, it's the same as a refrigerator. The QH is what you're looking for, and the amount of work that you have to put in order to do that is kind of along the same lines as this. It's a small amount of work that you put in order to get a large heat flow into the house. And because of that, a heat pump is highly efficient. I mean, obviously, if it's a Carnot heat pump, it's the best possible situation. Unfortunate that that is never the case. But nonetheless, a heat pump is a highly efficient piece of equipment and much more efficient than straight burning of methane or baseboard heating or anything like that. It's actually more efficient to do it that way. It's actually more efficient to take the energy that you would have put into electricity and then convert it into heat than you should take that energy and use it to run a heat pump. You'll actually get more heat. It's kind of a funny thing to think about, right? Okay. So, I was going to say something else about this, but I forgot what it was. Oh well. Let's do this. All right. Yeah, what was I gonna do? Let's take a look at a quick summary here. So this is gonna be, I don't want to do Carnot first though. I want to do, what is it? What do we call that? I'm totally blanking on the word I'm trying to write. Dang it. I know what I want to say. All right, well, this is a normal. It's not the word I wanted to use, but okay, normal. So I want to just do a quick comparison of some of the things that happen when you take a regular heat engine like the ones that we would make, and you compare it to a Carnot. All right, so everything that's true for the normal one, for example, the efficiency, work divided by QH for a heat engine, would still be true for the Carnot cycle, okay? It would still, QC over QH. This would still work for the efficiency of the normal one, and it still will work for the efficiency of the Carnot one as well. But what won't work for the normal one is the Carnot efficiency, and that's only true for this. Okay, so remember, this gives you the idealized best possible efficiency when operating between these two temperatures. You can't do better than a reversible engine, and that is telling you that this is your ceiling. For the normal engine, you'd still write that QH is equal to QC plus W, and that's still true for the Carnot cycle, all right? I guess what my purpose is in doing this is telling you that there's really all of the stuff that we've used in order to analyze heat engines is still true for the Carnot cycle, but the Carnot heat engine, but the one thing that's new is this, okay? Everything that we had from energy conservation and efficiencies and that type of stuff is all still true for the Carnot cycle. It's not that you only use this for anything. You can use all of these for the Carnot cycle, right? But you can only use those three for just a regular heat engine, okay? So when you're thinking about what's going on with a Carnot cycle, remember that we can connect the operation of a Carnot heat engine to what's going on the PV graph, okay? And I wanted to make one other point about this. When thinking about our four thermodynamic processes, right? We had the isovolumetric, we had the isobaric, we had the isothermal, and then we had the adiabatic. Okay, so I'm just going to write the variable that's constant next to them, like so. Constant V, constant P, constant T, no Q. Notice, however, the no Q situation, what does that also mean? That means that if there's no heat transfer in or out, that means the entropy is constant, right? As you are doing an adiabatic process and you're doing it nice and reversibly, you'll be doing a constant entropy process that's known as being isentropic. That's also the word for adiabatic, right? Especially when talked about in a reversible sense. Notice that the entropy will increase for any of these other processes. The entropy increases for a constant volume situation because you put heat in. It increases during the pressure process because you put heat in to increase the temperature and the volume increased. Even if you didn't increase the temperature when it's an isothermal process, you still put heat in, right? And so one of the things I have hoped for you as we've gone along with this is that you've hopefully divorced the heat transfer from temperature. Heat and temperature are different, and we have to speak of them differently because they do different things. And unfortunately, when we talk about them in a common way, we say, oh, we heated it up. What that really means is we increase the temperature. So be careful about how you're thinking about temperature and heat. Constant temperature doesn't mean no heat. Adiabatic means no heat. Constant temperature means heat and work, same amount. Okay, so I just want to leave you with that. And so we will pick up with this tomorrow. I got one last topic to talk about with the second law and the thermo stuff, and I think we might just be finishing this stuff off on Thursday in the next video. So anyways, I hope you have a great rest of your day, and try to stay out of the reach of entropy's grasp. Unfortunate that it is inevitable that we will always increase the entropy. And when we go into class tomorrow, we will talk about some of the more interesting offshoots of the second law. All right, happy rest of your day, friends. We'll talk to you soon.